Okay, well, it is 9:02, so we're going to go ahead and get started, folks. Thanks for coming to this morning's Bureau seminar series. I'm Kelly Hattori, and today I'm hosting Dr. Peter Eichhubl, who is a researcher here at the Bureau. Just as a reminder before we get started, everybody, if you could please hold your questions until the end or type them in the chat box so that we can ask them at the end. That'll help us stay on time. And for those of you who won't make it through to the very end, a reminder that next week we're going to have Sandra Snabjørnsdottir talking about carbon mineralization. So today we're going to have Dr. Peter Eichhubl talking to us about his work in Caprock failure and possible implications for subsurface storage of things like carbon and hydrogen. So we're really excited to hear about his new work in this. Dr. Peter Eichhubl has a master's in geology from the University of Vienna and a PhD from the University of California at Santa Barbara. Before joining the BEG in 2006, he worked at Stanford University, Monterey Bay Aquarium Research Institute, and Texas A&M at Corpus Christi. Peter's research combines the fields of fault and fracture mechanics, geomechanics, and low-temperature geochemistry to address fundamental aspects of crustal deformation, mass and heat transfer in sedimentary basins, the effects of chemical mass transfer on the mechanical and hydraulic behavior of fractures and faults, and the chemical interaction between fluids and minerals. This research is of relevance to the production of geothermal and hydrocarbon resources, groundwater management, and underground storage of hydrogen. Fundamental aspects of this research have implications for the seismic and aseismic deformation of the Earth's upper crust, the interaction of subsurface fluids with the atmosphere and biosphere, and for energy resources. So, Peter, you are ready to go. You can share your screen and take it away.
Well, Kelly, thank you for the introduction. I was glad to fill in the slot as it emptied, as it became necessary to jump in. Let's see. Can you see my screen? Up. Oops. Here. Display settings. Am I good?
You're still in there.
Yep.
Now you are.
Yep, there you go.
Okay. So thank you all for attending this Friday seminar. This topic is work. First of all, I need to acknowledge my co-authors. This is work that was done over a couple of years now with Xiaofeng Chen, former postdoc, and Owen Callahan doing the majority of work here. John Olson being a senior co-PI in this project, and Tom Dewars at Sandia National Labs. This work, my interest in addressing caprock behavior goes back for many years when the CO2 sequestration research was ramping up. But funding to get to work on the topic of leakage, it took a little bit longer to get. So at one point we got an NETL grant to do this work. The majority, and this work was done actually a few years ago now. It's all the data have been published, but now some with the hydrogen storage topic, and us forming an industry consortium, have renewed interest in looking at this from the hydrogen perspective. But I should say up front here that the work that has been done, and the talk today is primarily about CO2. And the hydrogen part comes in at the very end. I will say a few words, but that's work that needs to be done. We haven't done yet. So it's a little bit of a teaser in that sense. And I hope, apparently it worked to get people into the room here. So I hope you don't mind me doing that, but primarily about CO2. And overall, the concern here is if we put fluids in the subsurface for storage, be it storing natural gas, CO2 or hydrogen, or even wastewater that's being injected, we want it to stay there. In case of natural gas and hydrogen, stay there until we want to get it back out, right? So we don't want it to leave the reservoir prematurely. And for all the buoyant fluids and also overpressured fluids, we do need a caprock. Caprock, or top seal as it's also called, to contain it in the porous formation that it is designed to stay. And in case of natural gas and hydrogen, also where we can retrieve it, right? So it shouldn't migrate out. And migration could occur either by porous media flow through even in a mud rock. Conceivably, you could have slow porous media flow. It could occur along fractures and faults. And in case of hydrogen, perhaps also by diffusion. That's something that our consortium will look into further. But for CO2, I think diffusion is not so much of a concern, the molecules are larger. The reason we are concerned about is fundamentally threefold. And I would put economics number one here. If you inject something, if you lose it, you lose money, right? So just the cost of injection mandates that you have a working Caprock in place. Mitigation costs money. So that's the number one. Even just the perception of leakage could cost you, it could cost you the license to operate, for instance. So that all comes down to money. Hazards, and maybe I put it secondary actually, but in some cases, I will get back to this. You could cause pollution, groundwater contamination. Groundwater, there's a formation water that's actually leaking with the stored fluid, not necessarily the CO2, but formation brine that's migrating along with it could contaminate the groundwater aquifer. So all those things need to be avoided. And on the right side, I have a little cartoon that shows, so the overburden is missing here. There would be at least a kilometer of overburden, CO2 injection well. You would inject supercritical CO2, which would pool underneath the caprock. Then you have the brine, the resident brine, and in between the CO2 would dissolve into the brine, and you would have this CO2 charged brine. So that's basically, we have three fluids to contend with, primarily the supercritical CO2, which is fairly dry, and the CO2 charged brine, which is fizzy water, right? And then the caprock. So when we talk about the risk of leakage, it's probably best to look first at natural gas storage, because that is an industry practice that has been done for, I guess, 100 years now, is widely practiced. You see on the left a map in the US with all the natural gas storage sites. There's lots of those. The green dots are the salt cavern storage, but all the red dots and the blue dots are porous media storage, either depleted oil and gas fields in the red, and in some cases, gas storage in aquifers. So this is widely practiced, and it's safely practiced. As an example here, I'm showing this dot here on the left. This is where Santa Barbara is, and it turns out there's actually a large storage field right underneath the university. And that's the red part here is the gas storage site. This is the university here. And my old office was right on top of this gas storage facility. So people don't know about it. So that's the way it's supposed to be. It's something that serves us, provides continuity in our natural gas supply, and we don't want to hear about it, right? So as a consumer. Unfortunately, occasionally, as with all industrial operations, things happen. And as far as I know, there's only one major incident in all those gas storage operations that I'm aware of. And that was on the left map, it would be in the LA area, one of those dots here, the Aliso Canyon leakage in 2015. And that was actually a casing failed, and natural gas escaped. The main issue here is obviously the methane that leaks to the atmosphere is a greenhouse gas, and it takes, I think the half-life of methane in the atmosphere is something like 7 years. So it takes years for that to break down. To my knowledge, nobody was hurt by this. But the bottom line here is any kind of storage operation is an industrial operation, and we need to be aware of the risks. need to be identified and safety protocols have to be in place. Just like bridges, right? We use tons of bridges, and occasionally they collapse, as it is in the news today. So, and CO2, well, we don't have the experience of operating CO2 storage at the same scale as we have with natural gas storage. One example that one could use is CO2 is released by volcanoes, and the picture here on the left is the aftermath of some natural leakage of CO2 from the Mammoth caldera in California. In this case, this looks pretty devastating here. What happens here is they get a lot of snow in the winter, and the snow on the ground traps the CO2 that's escaping from the ground, and that kills the trees. The concern for man-made structures would be that it accumulates in the basement, for instance. But let's keep in mind this is a nearly endless supply of CO2 because it comes out of a dormant volcano. So I don't know if this is a good analog for leakage from a CO2 reservoir. Conditions here are different. There's probably not much of a seal there to break. It's just produced from the magma chamber underneath and leaks up along faults and fractures. So maybe that's a worst case scenario. So the problem statement here is ultimately we need caprocks that allow stored fluid to keep in place. And we need to understand processes that would threaten the caprock integrity over long time scales. And in the case of CO2, it's a few thousand years. If we sequester CO2 in the subsurface, we want it to stay there for the rest of human existence, right? So we don't want to burden our future generations with dealing with remediating this. Now, seal risk assessment or caprock integrity assessment is well established for the oil and gas industry, because in that case, explorationists want to make sure that oil and gas was trapped in a structure before it's being drilled. And this similar approach is used there to evaluate if the risk of if the caprock or the seal is intact or not. Now, one thing that is different though from oil and gas is that CO2 interacts with the resident brine. It dissolves into it and can change the chemistry of the brine, and that can trigger chemical reactions. That's not something we worry with oil and gas, but with CO2 we have to worry about it, which brings me to the topic that when we evaluate caprock integrity for CO2 and for hydrogen, it's the same thing. We need to be concerned about chemical fluid rock interaction and how that interaction can affect caprock failure. Now, the topic of my talk today is how that chemical interaction would affect fracture growth. So that's the introduction here. And there's one other natural analog for this that some of us have worked on over the last decade. And it's really the only really well exposed outcrop study site for looking into those processes. And that's the Crystal Geyser at near Green River, Utah, where we have CO2 charged brine coming to the surface. It's actually forming a geyser, but that's coming out of an abandoned well bore. But there is natural seepage. You see here the bubbling up of the CO2 in little puddles, and you have travertine. And that site has been used to study fault-controlled CO2 leakage. So that's an oblique quasi-aerial view from Google Earth. There's the fault zone, there's the geyser here, and there are active and inactive CO2 seeps along the fault trace. And the CO2 is coming with brines from the Paleozoic aquifer, and then there is fresh water being mixed in from the Navajo aquifer, and it comes to the surface. And you see in the field, this is the Manco Shale, which would be kind of a caprock there. It's obviously breached, but we see fractures and they're altered by CO2. The other thing we see here is extensive alteration of the shales. So this is a piece of the unaltered Mancos. It's weathered, but it's not. It's still a dark gray to black mud rock. But then near the fault, it's bleached yellow and it has fractures in it, has calcite in it. So you see the replacement and infill of pores by calcite. So it's extensively altered. Now, the question is, we have published papers on this and it has been used as a natural analog for CO2 seepage. The question is if it's a good analog. And on second thought, it may not be, because there's a lot of water coming up and it's active over thousands of years. It has been dated 10,000 years actually, and single seep sites can be active for 1,000 years. That is not what we expect for a leaking CO2 reservoir. There wouldn't be that much water coming up and it wouldn't be active for 1,000 years, right? So this extensive alteration is probably not something that should guide us to evaluate CO2 leakage from a storage reservoir, even though we have done all the work on it. It was interesting, enlightening, but maybe not the best analog for an industrial process. Now, having said that, though, is do we need such extensive water-rock interaction to weaken the caprock? That's the main question here. Or are more subtle chemical effects sufficient to threaten the caprock integrity over engineering timescales, shorter timescales, not 1,000 years, but maybe tens of years or 100 years, right? So, well, let me make a detour here. It's already mentioned bridges here. We can't really see what's going on in a caprock in the subsurface, but in terms of understanding how fractures grow, we can look at engineering structures. And I will take here the example of bridges. They can fail because in some cases the load capacity is exceeded, like this truck on this little tiny bridge here. That is equivalent to injecting too much pressure in the subsurface and just rupturing the caprock by too much stress on it, okay? In some cases, bridges fail because the bridge is completely decayed, rusted away, and maybe, you know, I guess in this case, the truck was just too heavy, but maybe also the beams were rotten, right? But in other cases, that's not necessarily so. Bridges fail for no apparent reason here. And one is I can personally relate to is because as a child, I have driven over this bridge many times in Vienna. And it was 40 years old. It was in perfect shape and condition. And then one morning at 4:30, it collapsed. And there were only two vehicles on it, a city bus and a car. And the city bus was empty. So it was clearly not at peak load capacity. And there was no apparent reason that the river was not flooded, nothing. So there was no real reason that the bridge would collapse. What happened was that a crack had formed in the bridge support down here, just below this big arch here. And over time had sparred off part of the pillar here, which fell off and then the bridge collapsed. So that's just failure that accumulated over time in the support. It was not visible to the bridge inspections, so they couldn't see it. And then just one morning, out of the blue, for no apparent reason, it collapsed. So obviously the bridge is rebuilt. For those of you who have been to EGU, you have actually driven over the replacement bridge here in the subway train. The conference center is back here. And ironically, but they put this bus back into circulation after this incident here. Now, I couldn't help myself putting this here in. This is from today, from Pittsburgh. I don't know if people got harmed here. It looks pretty bad. But it's ironic to see a red city bus on a collapsed bridge here. So I guess things reoccur. Another interesting tidbit here is, you may remember this from last year, that the I-40 bridge in Memphis was closed for a couple of months because of a crack in the bridge structure here, in this beam here. And this was the picture that was shown last year in the news. There was this beam was completely separated by this fracture here. But ironically, they actually have an image from 2019, 2 years earlier, that shows this same fracture, but it hasn't gone all the way through. And unfortunately, the bridge inspector didn't look at the video that was collected. Otherwise, they would have caught this earlier. Luckily, this beam is not really load supporting. It's preventing the deck from flexing. So it's stiffening the deck. But it's under tension. That's why it's opening up. But it does not necessarily, the bridge doesn't collapse because of this. That's the good news. And they fixed it in the meantime. Interesting to see is it's obviously completely rusted out, which tells me that also the fact that it took years for this fracture to propagate across. It was not a sudden event. It grew over time. It probably grew by the chemical assistance of the oxidation here. So this is slow chemically assisted fracture growth. They think it started actually when the bridge was new. There was a welding flaw, and that flaw all those years, it was built in 73, I believe, over the 50 years has allowed the fracture to go across. Well, envision that a caprock may be just like this beam here. A fracture could grow in a chemically reactive environment. The humidity in the air and the rainfall would be sufficient. And then over time, very slowly, a fracture propagates across. Okay. You may have had something like this, where something hit your windshield in sometimes a random bullet falls from the air, hits your windshield, and then you get rapid fracture growth initially, and then if you don't fix it right away, it may actually stay for a few days or weeks. Sometimes you can see the fractures propagating slowly, especially when it rains and gets wet. And if you don't do anything, at some point it may fail catastrophically. This behavior of slow fracture growth and then rapid growth to complete failure is something we see in engineering materials very commonly. It's called subcritical fracture. And this is a plot of the stress that's applied to the fracture, the loading stress, and the velocity of the fracture propagating, but it's in log space. So in linear space, this curve would be curving up, but now it's shown as a straight line. That's the slow growth accelerating over time. So it starts here, then it gets faster and faster, but still slow. Then there may be a phase of constant velocity, and then all of a sudden it gets really fast. So the vertical part there would be instantaneous, right? Because the velocity is going to up to the seismic wave velocity. The acoustic wave velocity would be the upper limit. So this is called subcritical fracture growth. And Olsen has the equipment in his lab in petroleum engineering to measure this. So this is a glass slide that Xiaofeng used to observe the same behavior, slowly increasing the stress on the glass plate, and the fracture velocity is increasing, and then at some point it just breaks completely. Now the equipment that we use for this is called a double torsion fracture mechanics testing apparatus, and the samples are cut into thin wafers. They are about 1 inch wide, 2 inches long, and a few millimeters thick. And the apparatus puts a torque on the sample. So it pushes down in the middle here and pushes up here. And that allows a crack to propagate along the length of this wafer. And the neat thing about this is that we can submerge the wafer into a bath of water. So we can change the environment in which the fracture propagates. So we can change the pH of the water, we can heat it, we can bubble CO2 into it and change the pH. We can add HCl and make it even more acidic, or we can make it more basic. So the one thing we can do is we can change the pressure on this because it's open to the atmosphere. And there are two types of measurements being done. One, let me look first at the right diagram here, is we just load it until the fracture fails, there needs to be a seed fracture there, so it needs to be notched, so that's called pre-cracking, and then we load it at a fairly rapid rate and then measure the stress when the sample fails. That is called the fracture toughness, which is intrinsic to the material, so it's characteristic of the material. The other test is where we load the sample a little bit at a slower rate, repeatedly until the crack propagates, then we release the stress and let the crack decay, and then another loading cycle and decay, and another loading cycle decay. So repeated tests, and the load decay rate gives us a measure of the subcritical fracture behavior, which is called the subcritical index. It's the slope in this plot here. Okay, so this exponent here is called the subcritical index. That's what we measure with those repeated load decay cycles. And that is one way to quantify this subcritical fracture behavior as a function of chemical environment. Okay. Now we did this on 3 shales, and they are all commercially obtained because core samples don't provide enough material, and outcrop samples are usually too weathered. So this comes from a quarry, a piece of Woodford, a piece of Mancus, and a piece of Marcellus. And they were tested under room dry conditions, which has humidity, CO2 gas, which is very dry, DI water with nothing in it, or NaCl or KCl, and varying pH, room temperature, and 65 degrees. And the shales vary quite in composition. So the Woodford shale sample that we got is very quartz rich. You see it's 2/3 quartz, the feldspar and clays. The Mancus, or the Marcellus, is actually very calcite rich. It's almost a limestone. In this case, this particular sample has a lot of calcite in it. It's just the way it came, with some clays, of course, some feldspar. And the Mancus is maybe somewhere in between. It has less quartz than the Woodford, more has carbonate, feldspar, and clays. The clays in all those cases is predominantly illite, with some keolite. In those 2 guys, the Marcellus is purely illite. So a little bit of smectite in the Mancus, but overall they are not smectite-rich shales. The other thing we do is we coat the samples in, especially the clay-rich samples, in a hydrophobic agent. That is to avoid that the brine disintegrates the sample before we even test it. So the coating is applied over the sample, except for that induced seed fracture here. That's open to the fluid. So that limits the fluid interaction only to the fracture, which is more representative of the subsurface, because your fracture tip would be within a large layer of shale, and the brine would not necessarily get into the caprock from the underlying reservoir. So that's one way of making it more relevant to the subsurface conditions. Okay. So I'm showing you now. I'm not going to show you a lot of the data here. Just to give you a flavor of it. The first one here is the 3 shales as they behave with varying water content. So this is CO2, which is very dry, air, which has 50% humidity or even more some days, and then submerged water with the coating or without the coating. And on the vertical axis, you have here the fracture toughness, which describes the sudden fracture propagation behavior. And on the right side, it's the subcritical index, which describes the slow chemically assisted fracture growth. And you see that in all cases, for the Marcellus, maybe not some, actually not, but for the clay-rich samples, if you immerse them in water, it becomes easier for fractures to propagate, because the clays, and believe it or not, even the illite swells a little bit in the water, and it weakens the shale and allows fractures to propagate more easily. Okay, so there's actually more than, in this case, more than half reduction in the fracture toughness. The subcritical behavior, same thing. It decreases with increasing water content. Not surprisingly, the Marcellus less so because it has less clay in it. Okay, so this is primarily the clay interaction. Now, if we have water and change the salinity, as you may expect, for those of you who are familiar with how brines interact with shales, as we go up in the concentration of NaCl, both the fracture toughness, which is the short dashed line here, this is the fracture toughness, and the subcritical index go up with increasing salinity. Okay, so salinity, an increase in salinity actually makes the shale stronger. Okay, in the shale, in the clay-rich shales, not in the carbonate, which there's no effect there. And then I'm showing you one plot here for the change in pH. In this case, I'm showing this for the Marcellus, which is rich in carbonate. The upper curve here is for the fracture toughness. The lower curve is for the subcritical index. The fracture toughness is not affected by pH, but the subcritical index is. And if I go towards more acidic conditions, this rock gets weaker, right? It's easier to propagate the fracture. Why is this different for the fracture toughness from the subcritical index? Well, remember, this describes the rapid fracture growth, and this describes the slow fracture growth behavior. There is more time for the slow fracture growth for the water to interact with the rock. So there's more time for the chemical assistance to fracture growth. So this affects subcritical index, whereas it doesn't affect the quick fracture growth in the critical fracture growth. Okay. So this is for the carbonate-rich shale. I'm not showing it to you here, but the clay-rich shales that don't have or have very little carbonate, we don't see this effect. Okay. Now, you may wonder, well, this is all good and nice, but when they go to when they inject CO2 into the subsurface, it's actually supercritical CO2. It's not in gas form, it's supercritical, it's this supercritical fluid. How would that behave with the Caprock? This is something that we cannot test in Olson's lab because this setup there has no confinement. Tom Dewars at Sandia, he custom built a loading cell to do fracture mechanics tests in the confinement. Now, it's a little different testing geometry because of the reason to make it small enough to fit into the pressure vessel. It uses a different fracture geometry. So it basically wedges the sample along its axis. It's not the double torsion that we use in Olson's lab. It's called short rod geometry. There's a chevron notch here, and then it gets wedged open. It allows to measure the fracture toughness. It does not allow to measure the subcritical index. But using supercritical CO2, either in very dry form or saturated with water, quite replicates what we do with CO2 gas and water in the double torsion experiment. So the numbers are very comparable, except that dry CO2 dries out the shale rock even more so than the dry CO2 gas. So it's really sucking out the water out of the shales, and that increases the fracture toughness even beyond the values that we get in double torsion test. Okay, so dry CO2 has a strong dry out effect, which increases the fracture toughness. It makes the rock more resistant to fracture, whereas the wet CO2, when it's water saturated, behaves as if the sample were immersed in the water. Okay. Now, what does this mean for the Caprock failure? So this is not a trivial thing to address. You know, upscaling it from the experiment, one single fracture to the Caprock behavior, the larger scale, is not easily done. Numerically, if you want to simulate this numerically, keep in mind that those processes that occur at the fracture tip are at the micron to millimeter scale, whereas the Caprock is extending over hundreds of meters perhaps. So this is not something that's easily simulated numerically. One tool that we have is a boundary element code that John Olson wrote many years ago. It's called joints, and it allows to simulate fracture growth and accounting for the subcritical fracture growth behavior. Okay, the code needs its pseudo 3D. It's accounting for stress in 3 directions, but the fracture growth is limited to 2 directions. So in this case, we simulate the fracture growth in a vertical plane, which is what those little diagrams here represent. That would be the bottom of the caprock, that's the top, and the fractures are told to propagate from the bottom up. There are little seed fractures in there, they need to be there for the fractures to initiate. And then the code is allowed to run for, in this case, 1,000 time steps. They call it years in the code. I'm not quite sure if they really represent years. I would consider them time steps, okay? So it's not necessarily telling you when things happen, it's more giving you a comparison, a qualitative comparison, how fractures grow across the seals as a function of rock type in the horizontal and vertically fluid composition, going from dry CO2 to dehydrated water, water of varying salinity and varying pH. And this shows the final outcome. They look maybe very similar to you for the most part, but it's interesting to then see, and this is also something that joints allow, it can calculate a fracture permeability across those fractures. And you can show this over time, model time, as a function of the different environments and for the different shales. And there we see differences. So for instance, if I take the Woodford Shale, which is clay rich, we see that in the water-rich environments, the fracture growth starts early, and then permeability increases up to a point. If we do it in a dry environment, nothing happens for a long time, but then quickly the fractures grow across, and at the end, actually, the permeability is higher in the dry CO2 case than in the water-saturated cases. Okay, so that's very interesting. So even though the fractures start leaking earlier, but at the end, the permeability is higher for the dry case. The Mancos shows the same thing. In the Marcellus case, the water effect is not so pronounced, but the first thing that actually starts is the HCl fracture. They start here, and then under HCl environments, so highly acidic environments, which is actually more acidic than the CO2 would ever be in the subsurface, you get the highest permeability. So the fracture behavior is dependent on the fluid chemical environment. It affects how much permeability at the end, but it also affects the timing. When do the fractures start growing, and at what rate do they grow? Okay. Now you may ask, we have been asked, why do you study single fracture growth? Why don't you study the behavior of faults? Aren't faults the structures that control fluid flow? More importantly, a fault would be reactivated at lower injection pressure, then you would form opening mode fractures. For opening mode fractures, even subcritical fractures to form, you would have to exceed the fracture gradient, which in a CO2 reservoir, you would obviously manage the injection pressure, you would avoid that. But faults may reactivate. Now, I have to say this, fault surfaces by themselves are usually not fluid conductive. There's an example here from a mine where we did some work where we exhumed a shale gouge in the fault zone. There is no flow pathway here. It's perfectly sealed. What is conductive for fluid flow are fractures that form in the damage zone of the fault. And here an example of the Moab fault where we mapped the distribution of alteration of diagenesis, in this case, calcite precipitation, that is confined to locations where opening mode fractures form, and they form at specific locations along the fault, such as branch points or steps in the fault, or where the fault changes direction. Okay, so that's tied to the formation of opening mode fractures along the fault zone. So ultimately, it is the opening mode fractures that control the permeability of the fault zone. Same thing at Crystal Geyser. The seepage sites are where the highest intensity of fractures is because of fault bifurcation and complexity in the fault trace. Okay. So what are my takeaway points here? I talked a lot about bridges and windshields, but they are giving us some kind of more direct insight how structures fail. And that applies to caprocks as well. It doesn't have to be a wholesale chemical alteration. The bridge doesn't have to rust away before it collapses. It can collapse because of chemically enhanced fracture growth, which can go fairly undetected for a long time. And it's the same thing with rocks. The shale fluid interaction doesn't have to be very extensive for reaction-enhanced fracture growth, which is perhaps bad news because it would be hard to predict and hard to detect, right? So that's where what Catherine does with monitoring for CO2 at the surface or in aquifers, that's the way of handling this. Seismically, for instance, you would have a hard time monitoring this. And then understanding what those chemical effects are and how they are controlled by lithology, and maybe picking a sequestration site where the caprock is less prone to weaken under the chemical effects by the CO2 brine interaction, right? So we have seen that swelling clays may not be good. Very carbonate-rich caprocks may not be good either. Something that we did not observe, we don't have very smectite-rich shales in our samples, but while we see a strengthening because of dehydration, a very swelling clay, smectite-rich clay may actually contract and open fractures because of dehydration. So there's two effects that need to be accounted for. All this would be spatially variable because it depends on where the supercritical CO2 is, well, and where the CO2 charged brine is, right? So this could be spatially variable, and over time, as the CO2 dissolves in the brine and you push out the CO2 plume, this behavior could change over time. Okay, and as I said, yes, faults may be the host, but where those fractures occur, but ultimately it's fracture growth that controls the leakage behavior. Now, last slide, and I said I would say a few words about hydrogen. So all this affects is somewhat the same story, regardless of what you inject into the subsurface. Even producing water from formations and re-injecting changes the chemical equilibrium in the subsurface. As soon as you produce water, there's degassing, changes the pH, and that may be harmless. It may not be sufficient to cause much alteration. With hydrogen gas, that would be dry, would certainly dehydrate clays. There may be some other chemical interactions. They may be in part microbial. There has been work done on looking at those effects on the hydrogen itself, how the hydrogen composition changes. There has been done some work on the reservoir rocks. As far as I know, not much has been done on caprocks. So that is work that's ahead of us. There's also the effect of cyclic loading. This is not something we have for CO2. You just inject once. But for natural gas and hydrogen gas, you would be injecting, producing, and that causes load, unload cycles that may also enhance fracture growth. It's a fairly universal issue to deal with. Hydrogen may be less reactive than the CO2, but in detail, this needs to be looked into. And then last but not least, this is why we got started actually working on this. In the first place, we are also interested in natural fracture growth in the subsurface or geologic timescales. And this type of chemically assisted fracture growth is probably the rule and the exception. I would think that except for earthquakes along an earthquake fault, slow fracture growth driven or at least assisted by chemical reactions is probably the norm. With this, I would like to open the discussion, if I think we still have time.
Yes, we have time for several questions.
Okay. Let me perhaps unshare here. All right.
Well, thanks for a really cool talk, Peter. If anybody has any questions, feel free to unmute or raise your hand or type in the chat, whichever floats your boat. If you type it in the chat, I'll read your question for you.
I also take questions about bridge failure, but only to a very limited extent.
Jean E in the chat says, were horizontal stresses considered in the simulations with joints?
So the whole simulation is done with prescribing a horizontal strain on it, an opening rate. That induces horizontal stresses, but the boundary conditions are displacement, not stress in that joint simulation. So we have a constant displacement rate in the horizontal direction and basically pull the material apart. So the answer is yes, but it's not the controlled variable, it's displacement.
I saw Julia Forsyth, you unmuted. Do you have a question, Julia?
Oh, I'm sorry, I don't.
Oh, okay.
I just hit the wrong button.
Very good.
Hey, Peter, this is Dodie.
Dodie.
Hey, nice talk. Hey, I have
Thank
a
you.
question on that. The Mako shale. You know, the unaltered shale is kind of like, I don't know. I didn't see the mineral. It was like 70% illite, 20% quartz, kind of mud rock. But then on the altered side, it was, I mean, it was predominantly calcite. Like, it looked like it was like 70%. Is that just calcite cement, or is that like alteration from the primary minerals?
I don't know. So this is the Mancos shale and outcrop is somewhat different than the Mancos that we used for our analysis. In outcrop, it has much more smectite than the one we purchased from the lab, and that may be perhaps reverse weathering. Going from illite to smectite. The replacement by calcite, it doesn't have that much pore space. So if it's just infill of pore space with calcite, you wouldn't get that much calcite, right? It doesn't have 70%, something like what you said, 70%, you know? So I don't know if it's a replacement or if the calcite is actually dilating the rock as it is precipitating calcite in it, you know? I mean, we can only go, this is, we only have percentages, right? So we don't, so this, I don't have the answer to your question. Yeah, I was wondering about the same thing. It's really peculiar, right? That you have that much calcite in it. It's based on XRD, you know how precise that is. It's at least, you know, plus minus 5%, you know, so it's not precise, but maybe it's 60%, it still would be a lot, right? And it does not have any, this was a pure shale sample. It did not have any visible fractures in it that are cemented with calcite. We made sure of that too, right? So it is pore filling cement, but why it's that match, I don't know. Good question.
Thanks. I mean, to get that percentage of calcite, you'd have to have not just, you know, large pores, but all your microporosity essentially filled by calcite.
Right, and I don't know. I mean, I think actually what's happening here is, well, either we are dissolving silicate grains and replacing them with calcite. That's possible, right? Probably, and then maybe, yeah, I don't know. I mean, that's probably what's going on, you know. But yeah, we haven't looked in this in detail. It's curious.
Yeah, that's good though. That'll be important though. If that's a continuous process that you keep adding calcite to the matrix, that's, I mean, that'll change the rock properties and, you know, how it's going to fracture over time with, you know, more CO2 injection. Pretty dynamic.
Again, keep in mind that this side, there's a lot of water coming with the CO2, right? It's water with CO2 in it, right? So that is very reactive. Not necessarily the case with CO2 storage reservoir, depending on where the failure occurs, right? If it is occurring where the brine is, then yes. But then you wouldn't have 1,000 years for the rock to react, right?
Thanks.
At least not in our lifetime.
Sounds like a problem for future.
Right.
Alessandra asks, have you considered the stress and I can't say that word, anisotropy effect on fracture growth rate?
So in this case, again, the joints models are with the displacement rate. There is a stress applied in all directions, so it's pre-stressed, and then we reduce the horizontal stress in the x-axis by prescribing a displacement rate. So yes, there's an anisotropic stress field. We are not varying the overburden stress law. So this is held constant. The only thing that's changed is the horizontal stress. So in that sense, no, we did not investigate this detail, but John Olson has written papers on this, and yes, it affects mode 1 fracture growth because a single fracture, not so much, but when the fractures connect and link and curve, they are allowed to curve, then in this case, the vertical stresses would matter, and the stress anisotropy matters. That's something I can refer you to some papers by John Olson. But we didn't investigate this in our case, because it has already been done. So
Okay,
in other words, the more anisotropic the stress field is, the more planar the fractures are. If it's more isotropic, then the fractures tend to curve more, and you get a more irregular fracture network.
Alessandra also asked if you have studied mechanisms that may arrest fracture growth.
Well, I mean, as I said, you know, there are reactions that are strengthening the rock, right? I mentioned the increase in salinity. I mentioned an increase in pH with the carbonate-rich shales, or the dry out. That would arrest the fractures, right? So it's not necessarily enabling fracture growth. It can go the opposite direction. That's very important to emphasize. I mean, there may be more the research was motivated by understanding what makes caprocks fail. But at the end, what we found is actually a lot of those chemical interactions would have the opposite effect, right? They make the caprock stronger. I think that's a very important part of this. But it's complex in detail, right? It's very dependent on the chemical environment and the rock composition.
Yeah, very complex. Sonia Marino asks, how reproducible are the fracture permeability measurements shown for the 3 shale examples?
So they are calculated, right? They're calculated based on the joint simulations. The joint simulations are actually, if you rerun the same loading snare with the same seed fracture, the same place, you would get the same results. So they are fairly prescribed in that sense, you know. You can obviously, the seed fractures are created randomly, but once they're there and you load them at the same loading configuration, that's what you get. And then, so it's, we have varied some parameters. We have done some sensitivity tests. Keep in mind, this is not quantitative. This is just to illustrate the range of effects it could have. So it's useful to compare the different chemical environments and different rock types. I would not give too much meaning to the time scale, for instance, or even the absolute numbers in permeability. That's not what that type of simulation is supposed to give you.
Okay. Shengpeng says, are these he wants to know if these experiments were conducted under reservoir pressure condition or ambient condition. So
the double torsion tests are ambient conditions with the exception of the increased temperature. The supercritical CO2 tests are done under reservoir conditions. 70 degrees and yeah, I don't remember the pressure of it. Yeah.
Great. Sue Havorka says she has a comment. So Sue, if you want to unmute and ask your question or have your comment.
Yeah, I'm having trouble typing it fast enough. Yeah, Peter, thank you very much for this talk. I wanted to say, you know, what you're talking about is expected and not a showstopper. And the reason is because the permit that we get for CO2 storage, EPA UAC Class 6 permit, defines a confining zone. So we expect the lower part of this confining zone to do all the things you're talking about, interact with the CO2. The issue would be, the thing that you have to do to get a permit and also to get a functioning site to show that it's not going to react. This rate of fracture propagation and chemical reaction through, it's not going to be so fast that the CO2 comes out of the top. So you know, we want to understand these processes and rate, but I don't think it's you know, it's not a showstopper that the the shales are reactive. I mean, that's to be reactive, right? So you're getting rates of processes, yay. But we want to show that those rates of processes don't propagate through a system of multiple beds of X thickness at a rate that would be such that the leakage would occur.
Right, absolutely. So that's where the rate of subcritical fracture comes in, right? Now the challenge here is to go from this numerical time scale that I was showing, I call it model years or increments of loading, to an absolute time frame, in years, right? That is obviously a challenge, because it's going from the lab experiment and the joints model to a field scale, that upscaling, that's tricky,
You might also consider the change in state of stress to the beds immediately overlying because of the injection.
Yes, so
water
this
pressure is going to dome, and it creates a change stress condition. And there was some nice Nicholas Espinosa had some nice new assessments of modeling techniques to look at that stress propagation, constrained from some of our experiments. So it was our field experiments, so it was very flattering. But so it might be interesting to combine your concept with his concept.
Yeah.
Great.
Well, again, so this is numerically not so. So a boundary element code cannot have a heterogeneous stress distribution. It's imposing the stress or the displacement conditions at the outside of the box, right? So you cannot have, say, polarlastic effects in it, or the higher pore pressure in the vicinity of the injection well bore compared to the periphery. That you can do. So if you go then to final elements, dealing with the reactive fracture growth is tricky because if you model something at the reservoir scale, you would not be resolving what's going on at the fracture tip, right? So this is, I would say, this is it's a simulation challenge to do this properly. But yeah, I agree with you. There's still a lot of opportunity left to do this, and even if it's just enlightening us, to understand those processes better, that would be great. Not as a routine tool that you would do this for every CO2 reservoir, but just to understand, what is the true time scale of this? And as Sue said, if those fractures propagate over 10,000 years, we don't worry about it, right? So, and the same thing with the windshield, right? I mean, you can drive with this broken windshield for a long time and nothing happens. And they're very nonlinear, those things. So sometimes then all of a sudden the windshield shatters, right? So predicting all this nonlinear behavior,
It's challenging.
Yep.
Well, we've hit 10 a.m. and Peter, I know that you've got another commitment, so we're going to have to stop all the questions there. But thank you again, Peter, for a really interesting talk with a lot of really cool stuff to consider. I know that a lot of people got a lot out of it. So thanks for stepping in again to help fill our opened up schedule. And just as a reminder to everybody, next week, we will have Sandra Snaborn-Stutter giving a presentation on permanent CO2 storage through mineralization. And I'll see you guys next week.